for the first lesson in Chapter 8, we're going to deal with similar polygons. This is page 223 of your student journal. I'd like you to read through, just kind of look at the vocab words, so as we come across them, you can come back here and make any notes you need. And then I want you to read through the bottom page 223 on your own, and then take a look at page 224 and read through that as well. Okay, so you have a couple theorems there. All right, off you go. Make any notes you need on it. Okay, before we go through those, I want you to tell your neighbor, just quick summary, what each of them says in your own words. Don't just read it verbatim. What does it mean? What does it say? Okay, here we go. Corresponding parts of similar polygons. Okay, so what this is saying right here is if we have two similar polygons first, their corresponding angles are congruent. Okay, angles don't measure when the figure is similar. So when we did reductions and enlargements earlier in the year, angles always stayed the same. Second, the ratios of their corresponding side lengths give you a constant value. They will give you the same ratio, meaning they are proportional. So if I were to look at the length of A and compare it to the length of KA, okay, they would be proportional. So CB to FE, I guess, if you want to think of it that way. Okay, and that's going to give you the same fraction as if you were to compare CA to FD. And the same fraction as if you were going to compare AB to DE. Okay, they would all give you the same fraction, meaning they all give you the same constant, which means their scale factor is that constant. Yes?
So you're saying that the angles would always have the same measure even for every?
Probably the best example for you guys to think of when you're thinking of angles not changing in a dilation is if I drew this figure right here and I told you it was a rectangle. And then I drew this figure right here and I said it is 3 times, it's been dilated by 3, or by 2, let's go with, okay? It's also a rectangle. The rectangle, right, the shape you've been dealing with for a long time, their angle measures don't change when they get bigger or smaller. They stay the same. Okay? Yes? Okay. Yeah. All right. Moving on. Next page. Page 224. Give it a go. Looking at that, we've got our perimeters. So perimeter really is just saying the same thing. It's saying, hey, if you have a scale factor, like if the scale factor for, if I was to compare PQ to KL, so let's call this maybe 2, and we'll call this one 1. Okay, that scale factor would be 2 over 1. All right, well, if I made all of these sides twice the length, so if I call this one like 6, this one would have to be 3. And if I called this one 4, this would have to be, actually, let's make this one 8. 4. And let's call this one, what do we want to call this one?
4.
About, can we call it 5? No, that'll give us a fraction. Let's call it 4. Okay, this is 2. Okay, so we have 2 plus 6 plus 8 plus 4 is 20. Thank you. So the perimeter of this equals 20. And 4, 3, 2, and 1 is? Perimeter of this is 10. And so I've added those up, I get 20. And I get 10. 20 divided by 10 is 2. You get the same scale factor. Okay? You get that same ratio there. So perimeter-wise, and the reason that is because when you're dealing with perimeter, you're dealing with linear measurements. So you're not squaring anything. You're not cubing anything. You're dealing with just the same length. So perimeter and side length, you're dealing with the same, so you get the same scale factor. That changes, though, when you go to area. Notice if I figured out the area of this, if I said, hey, this is, let's go back to our 1 to 2 ratio. All right, and I told you the area of this shape right here is 16. That means when I'm actually calculating, when I'm having to figure out the area of this shape, we'll call it x, I would have to actually figure out the square of that, ratio. So the first thing I'd have to do is I'd have to say, well, KL to PQ, that gives me a 2-to-1 ratio. But to find out the area ratio, I have to square it. So rather than being 2-to-1, it's going to be 2-to-1 squared, or 4-to-1. So my area ratio is the square of the perimeter, or the side length ratio. Okay? So if I know the big the big shape is 16, and I want to know the small shape, I have to use this proportion. Okay? This proportion would mean, in this case, we could cross multiply and divide, or you could say, hey, 4 times what is 16? 4, so 1 times 4 is 4, thank you. Okay, so the area of this one is 4. Okay, x would have to equal 4 to make that a true statement. And by the way, that's area. Volume is measured in what type of units? Cubic. What are you going to have to do to volume? You're going to have to cube your similarity ratio. Yeah, to the 3rd power. Okay, to kind of summarize it, if you want to take some notes on it, if I am comparing things, if I am thinking in terms of similar, unbelievable, use a pencil, all right. Okay, if I'm dealing with similar figures, and I am comparing the perimeters, our ratio, if we call it A to B. If I then go to area, I have to square it. I would then have A squared to B squared. That would be my ratio for areas. Now, I haven't seen in this textbook them use it, but you will eventually use it. If you're dealing with volume, you're going, and actually the arrow shouldn't go from there. It would be A cubed to B cubed. You would have to go from here and cube it. That makes sense? All right. And that's to help you find your correct measurement. All right. Not as cool looking as what they give you, but let's try some of these out. Let's see if we can apply some of this. Go to page 225 of your student journal. I'll be around to answer any questions you have, but I want you to work through page 225 with your groupies. Okay? Give 1 and 2 a go. If you get more time, you can keep going, but I'll get those answers up here in a minute after I walk around and answer questions. Off you go. Okay, so first thing, you want to keep them in fraction form if you get a fraction. But number 1, you're comparing your lengths. So if I have this length right here, the shorter side of a rectangle, it compares to the shorter side of the bigger rectangle. So I have 3 is to 2, as 7 is to x. Cross multiply, x times 3 is 3x, 2 times 7 is 14. Divide, 14/3. Hey, Alex. 4 2/3 would be fine. However, usually in algebra, you use that number somewhere else, so you'd probably change it back to 14/3. So I just left it there. 4 2/3 would be okay, though. I know if you're doing this on the computer, you're going to probably want it in 14/3. Okay? What's that? And number 2, once again, comparing, look at your angles may help you out. So from 1 mark to 2 mark, that is 20 to 8, or 8 to 20 if you go that route. And then you had to have x to 25, 1 to 3, 1 mark to 3 marks, okay? And then cross multiply, you get x equals 10. So you're dealing with linear measurements, no squaring involved there. Okay. Questions? All right. Try 3 through 5 if you haven't done them already. Okay, so make sure we're good. Scale factor from ABCDE to KM, KLM, and P, you're getting bigger, correct? So would it be 2 over 3 or 3 over 2? Have to be 3 over 2 because you're getting bigger. Okay, that number is greater than 1. Okay, and that can seem confusing because when it says here to here, sometimes you just go, well, I take that number, put it over that number because that's A and that's K. Okay, however, you have to think I'm getting bigger, so my scale factor has to be greater than 1 there. Whereas you're going the other way, it would be less than 1. And you could have compared any side, okay, that you had numbers with. It just seems those are the easiest right now, and we're not actually given the x's and y's. So, okay, so find the value of x. We'd have to use our scale factor. So 2 is to 3 as 1 is to x. So small on top, so small and small, big and big in terms of the shapes. Small shape, big shape. So we get 2x equals 3, so x equals 3 halves. If we're figuring y, use the same ratio. 2 is to 3 as 3 root 2 is to y. Cross multiply, we get 9 root 2 equals 2y. So y is 9 root 2 over 2. And then if we're finding z, remember angles don't change. Z equals 45 degrees. Go to its corresponding angle. Okay, questions on that one there? All right. Find your perimeter, the ratio of the perimeters, and then the ratio of the areas if you haven't done so. Okay, we get 6 plus 3 root 2. Can we combine the 6 and 3? Don't make the mistake of putting 9 root 2 there, right? Can't put those together. So adding up all our sides. So 3 plus x we found was 3 halves. Plus 3 halves. Plus 3. Plus 9 root 2 over 2. Okay, we've got all of our sides here. That's 1 1/2. 1 1/2 is 3, plus 3 is 6, plus 3 is 9. So 9 plus 9 root 2 over 2. Well, that is not 18 root 2 over 2. Ratio of the perimeters is the same as the ratio of the area, so that would be, or the ratio of the perimeters same as the scale factor, so it's 3 over 2. However, the areas, we've got to square that, so it's 3 over 2 squared, which is 9 over 4. You can also see this as, may look like that. It may be, you'll sometimes see it written like that. Same thing. All right, questions? Okay. While I'm handing out your tests, I want you to do this problem with your groupies. Handing back your tests there. I want you to do that problem there with your groupies. Hey, what's our perimeter similarity ratio? Yeah, 10 to 5 or 2 over 1. What's our area ratio then? Area would be, we've got to square it. So it would be 4 to 1, not 4 to 2. 4 to 1. Okay? So make sure that you square this. You have to go 2 to 1, quantity squared, to get that 4 to 1. And then you could set it up. If the area of the big is 36, and you want the area of the small, make that y. Cross multiply, you get 4y equals 36, so y is 9. So the area of the small is 9 square centimeters. Any questions there? How many got it? No one got it. Oh, some of you got the first part. How many got the area ratio? Okay. What kind of questions do we have? None? Okay. Go ahead and finish handing out those tests. Go ahead and do example 6. Are they similar?
Yes, yes they are.
Yes? Are we sure? Yeah? Looks like we have two angles that are similar. 8 is to 12. Is that true? Are we comparing the correct things?
The bottom of BA or AB.
Okay, so you're going 12 to 8. So that one to that one. Everyone agree?
No. It's PK.
PK?
My PK is AB. That's the same.
You guys agree?
Yeah.
No.
All right. Okay. Hey, are the sides proportional? Yes. What's our scale factor on each of them? 2 to 3 or 3 over 2? Okay. Does that necessarily mean that they are similar? Yeah, they could have different angle measures, right? We know that one angle is congruent, but in order for two figures to be similar, their angle measures must be preserved. They must be the same, so we would have to know that this one is congruent to that, to its corresponding over here, say that one. We'd have to know that this one's congruent to its corresponding, and so on. In fact, it doesn't really look like it if we're just doing an eye test, which isn't a good thing to do, but it definitely, we cannot say they are, because we don't know that the angles. Okay? In this case, it doesn't look like they are. So just because you have a similarity ratio doesn't necessarily mean that they are congruent or that they are similar. You have to be able to preserve your angles. Yeah.
So if like the angles are congruent, then
Hey, any other questions? All right.